In this video, we're going to take a look at voltaic cells. Now, before we dive into what voltaic cells are and how to do cell diagrams with them, I think it's just worth noting that voltaic cells are usually called by many different names. They can sometimes be called electrochemical cells, or they could also be called galvanic cells. So they all mean the same thing. Sorry, just making sure I'm spelling that right. Okay, so galvanic cells or electrochemical cells. They all mean the same thing. Okay, so just worthwhile noting that there is different terminology for these out there depending on where you are at. Okay, so before we kind of get into what a voltaic cell is and what it looks like, I do want to start out with a comparison of different types of electrochemical cells because in later lessons we're going to learn about another type called the electrolytic cell. So it's worthwhile just doing a comparison now so we get a feel for what these cells look like. Now, to start off with, a voltaic cell is based on a spontaneous reaction, whereas an electrolytic cell is based on a non-spontaneous reaction. So that's a big difference between the two. Voltaic cells convert chemical energy into electrical energy, whereas electrolytic cells do the opposite. They take electrical energy and convert it to chemical energy. Now, in terms of the anode and the cathode, they both, in a voltaic cell and an electrolytic cell, both of these have oxidation happening at the anode. But the charges change. So in a voltaic cell, it's a negative charge, and in an anode, it's a positive charge. And we will see why this is the case when we get into both types of cells separately. The cathode, on the other hand, is where reduction takes place. In a voltaic cell, it has a positive charge. In a cathode, it has a negative charge. So the way I remember anode and cathode and what reactions are happening there is I remember our good friend, the red cat. So reduction happens at the cathode, and then if you remember that one, then the other one happens at the anode. So oxidation happens at the anode. So kind of silly, but can help you remember where reduction happens and where oxidation happens. Okay, so what is a voltaic cell? We know that it takes chemical energy and it creates or converts that to electrical energy. So how does it do that? Well, it kind of has three main components and uses the oxidation and reduction half reactions in order to create electrical energy. So the first component is it consists of two half cells. So in a voltaic cell, this over here would be considered one half cell, and this on the other side would be considered the other half cell. So there's always two half cells, one in which is the anode and the other is the cathode. Now, in order to connect the two circuits together, we also have electrodes connecting them, and we usually include a voltmeter so we can see how many volts we are creating from our chemical reaction. So our voltmeter is here. Now, if we just had that, the two half cells and the electrodes connecting the two, we don't complete the circuit. So in order to complete the circuit, we need something called a salt bridge, and that is this piece here. And it's just a tube, and it's filled with a salt solution, something that is not going to be your strongest or strongest oxidizing or strongest reducing agent, because you do not want it being part of your reaction. And it connects the two half cells and essentially connects the circuit. So salts like sodium nitrate, sodium perchlorate, potassium chloride, potassium nitrate, these are all really great salts that you can use for your salt bridge. Okay, so knowing that now, we have to be able to construct diagrams for voltaic cells. So if, for example, I asked you to construct a voltaic cell between copper and zinc, then you will need to go through all of these steps to create the diagram. So you would start out by drawing this sketch here. I'm obviously not going to draw it, or else this video would take forever. And then we're going to start by deciding that, and it doesn't matter which side you pick, but we're going to say the anode is this left side here and the cathode is the right side. Okay. Now we know a voltaic cell, the anode's always a negative, so I'm going to put a negative there, and our cathode's always the positive. And then at the anode, oxidation occurs, so I'm going to get ready to write my half reaction there. And then at the cathode, reduction happens. So I'm going to get ready for my half reaction there. Now this is where now I need to go to my redox potentials chart and find copper and zinc and figure out which one is our strongest oxidizing, strongest reducing agent, because we want to have this set up so that it is a spontaneous reaction. And if you take a look at our table, the copper is going to be our oxidizing agent, so it is going to get reduced. And our zinc is our reducing agent, so it is going to get oxidized. So make sure you take a look at the table and understand where that is coming from. Okay, so then reading from our table, our copper is being reduced, and it's going to be reduced going from copper 2 plus ions. We're going to gain 2 electrons, and we're going to create solid copper. Now, I'm picking the 2 plus ion here because most likely this solution we have in here is something like copper sulfate, or it might be copper 2 nitrate, something like that. Okay. It doesn't really matter what this other ion is. We know that we just have a solution of copper ions. And then on the other side, we have our oxidation half reaction. So this is going to be our zinc, and this is going to give us zinc 2 plus ions and 2 electrons. Okay, so let's label some stuff in here. So this is our solid zinc. And our reaction is saying that that zinc is going to react. It's going to produce 2 electrons. And then it's also going to deposit zinc 2 plus ions in solution. Again, this is probably a zinc 2 plus sort of solution. It might be a nitrate, might be a sulfate. Who knows? It doesn't really matter. Once this oxidation half reaction has happened, these 2 electrons flow through the voltmeter and flow through to the cathode. Now, it's important that you draw in the arrows to show the direction of electron flow. And so we're just going to even label it that it's an electron flow. And then the 2 electrons are coming down in through here. And in the reduction half cell, we have copper 2 plus ions, and it's going to pick up the 2 electrons to create solid copper. So over time, what you would see is this zinc electrode would break down. And because it's basically eroding to create these zinc 2 plus ions, and then over time, you would see copper being deposited at the copper or the cathode because it's taking the copper 2 plus ions from solution and depositing it onto that electrode. Now, like I said, the salt bridge is important because if we just had this, eventually the reaction would stop. It would not continue to flow. So we're just going to pick salt, any salt really, it doesn't really matter. And we need to show the flow of ions to both sides. And essentially what this is doing is making up for the imbalance in charges in order to create something balanced so that the electrons will continue to flow. If we look on the oxidation side, we're depositing zinc 2 plus ions in there. So in order to kind of neutralize that, the chloride ions are going to flow into that half cell. And that's going to help balance out that buildup of positive charge on the oxidation side. And then the opposite on the other side, the copper 2 plus ions are being removed. So we need to replace that positive charge by having potassium ions going into there. The last thing we need to mark here is our overall reaction. And that's just balancing our two half reactions together. I'm just going to skip the state symbols, but you would want to put those in just for the sake of keeping this video short. So we would take copper 2 ions and zinc, reacting to give zinc 2 plus ions and copper. Now, just quickly, all of that entire diagram, and you do have to have that in all of those pieces of information to have a complete diagram, can be summed up in a single line. And so this is our shorthand notation to show what a voltaic cell is and what's happening. Generally, with our shorthand notation, you list the oxidation first, or your anode, and then your cathode, or your reduction. And you show what you're starting with initially, so zinc, what it's producing, zinc 2 plus ions, and then what's being reduced, the copper 2 plus ions, and what's being created, the copper. The double line here shows a salt bridge. And then the single lines are just kind of denoting the difference between the electrode and the electrolyte solution. Okay, so if you ever want to write in shorthand or want to interpret the shorthand notation, this is how you would do that. Finally, just really quickly, there is another setup for voltaic cells, and this one's kind of neat because it doesn't require a salt bridge. It's called the porous cup, and it's this cup that goes inside another sort of glass beaker or something like that, and it is porous, which means that ions can flow in and out of it. Generally, you set up your cathode inside your porous cup and your anode on the outside of your porous cup. And then because you have the ability for ions to flow back and forth, there's no need for a salt bridge. So it's kind of a neat, actually an easier setup to do for a voltaic cell than having to set up everything with two different half cells plus your salt bridge. So this one's kind of my choice and the way I kind of like to set up my voltaic cells if I have to set one up. That's it then for this video. Let's move on to our next task.